Hi everyone. Today we're going to be completing our notes on section 6.3, which is on exponential growth and decay. I want to start off with this warm-up. You're buying a new car and you want to learn how the value of the car will change over time. Insurance actuaries predict the future of the value of cars using depreciation functions. One such function is applied to the car whose declining value is shown at the right. So if we take a look at this image to the right here, we see that at the start, at 0 years, the value of the car is $10,000. Therefore, this is the buy it now price for a new car is $10,000. After 1 year, we see that the value of the car decreases by about 1,480. Okay, it continues to decrease year after year, and after 4 years, we're almost at about half of the initial cost of the car. So part A, I want to describe how the value of the car decreases from year to year. So again, as we look at this, from year 0 to year 1, we're decreasing by 1,480. From years 1 to 2, we're decreasing by about $1,307. From years 2 to 3, we're decreasing by $1,113. And finally, from years 3 to 4, we're decreasing by about $890. So we can say that the value over time, the value of the car depreciates over time. So it depreciates. And what that means is it's just less value over time. Okay. So what kind of function would model this pattern here? Well, if we look at the rate of change here, as we look at the value of the car from year to year, this is not decreasing by a constant rate. It's changing how much it's decreasing by. So we know that it can't be linear. Well, we know that what we're studying this year is another type of function. This function can be modeled using that function, an exponential function. Okay. In part C, given your answer to part B, what's needed to find the function the actuary is using? Well, in order to find the function that models this behavior, we need to know what percent the car is depreciating each year. If we're able to find this percent, how much is decreasing per year, we can come up with an equation, a rule. We could graph it, write a table of values. We can find the value of the car for any given year, given that mathematical model. Okay, so now I want to just do a quick review of exponential growth. Given the function y equals 5 times 2 to the power x, we're going to fill in the table of values and graph it below. So if I plug in, we'll start with 1. So 5 times 2 to the 1, this would be equal to 5 times 2, or 10. Okay? 5 times 2 to the second would be 5 times 2 squared, or 5 times 2 times 2, which is equal to 20. 5 times 2 to the third is equal to 5 times 2 times 2 times 2, which is equal to 40. And when x is equal to 4, we get that the function is equal to 80. So we see that this function, as we move down the table, is doubling. We would expect as x equals 0, the initial value, 0, we would expect this to be equal to 5 because we know that each row as we move down the table doubles. We also know that at x equals 0 is our y-intercept, and so that tells us that our initial value is 5. If we were to plot a few other points like -1, -2, and -3, if we were to evaluate these, so we would get 5 times 2 to the -1, this would be equal to 5 halves, which is about 2.5. If we were to plug in -2, we would get 5 times 2 to the -2, which is equal to 5 fourths, which is equal to 1.25. And finally, if we plug in 3, we would have, -3, then we would get about 5/8, or 0.625. Okay, so let's go ahead and plot some of these. We have our initial value, 0, 5, or y-intercept. And then we have 110, which is up here, 220, which is all the way up here. And that's all the points on the positive x-axis that we can graph. On the negative x-axis, or left-hand side, we have 5 halves, which is 2.5. So negative 1, 2.5. We have negative 2, 1.25, and negative 3, 0.625. So these values here. All right, so go ahead and sketch in that graph. Connect all those dots, and remember this curve's upward. Don't forget we have a horizontal asymptote, a y value that the function approaches but never reaches. So try not to cross that x-axis. And I'm going to go ahead and graph that asymptote as a dotted line. The equation for this asymptote is y equals 0. All right, go ahead and flip the page. Now I want to talk about exponential decay. Now this is going to look really similar to what we've studied already, but now we're going to be using this interest model, similar to the one that we discussed in the warm-up. So given this function, y equals 4 times the quantity, 1 minus 0.5 to the x, fill in the table of values. Well, looking at this equation, I noticed that we can simplify what's in the parentheses. This would be equal to 4 times 0.5 to the x. 1 minus 0.5 is 0.5. And so I know that 0.5 can be rewritten as 1/2. And because 0.5 or 1/2 is less than 1, I know that this is going to be exponential decay. All right. So let's go ahead and plug in some values into this equation. Our initial value, where x is equal to 0, is going to be 4. So writing that out, 4 times 0.5 to the 0 is equal to 4 times 1, or just 4. Plugging in 1, we get 4 times 0.5 to the 1 is equal to 2. 4 times 0.5 to the 2 is equal to 1. Plugging in 3, we get 4 times 0.5 to the 3, which is equal to 0.5, or 1/2. And then finally, 4 times 0.5 to the 4 would be half of that, so 0.25. Okay? So if we plot these points, here we have 0, 4, that's our initial value. We've got 1, 2, 2, 1, 3, 1/2, 4, 1/4. If I were to follow this pattern, I know that negative 1 is also going to hit the point 8. So negative 1, 8. We would do negative 2, 16. Right? We would continue that pattern on the left-hand side as well. All right, so go ahead and extend that graph. We can see our exponential decay here. And similarly to the last one, we have an asymptote at y equals 0. Okay? So this is going to be exponential decay. It's decreasing over time. So why did we write it this way here? We have 1 minus 0.5 to the x, instead of just writing it this way, 0.5 to the x. Well, the reason why is because the way that we modeled it this way is compound interest. Compound interest is the interest that's paid on both the principal and on the interest that has already been paid. The principal investment is the initial amount. So when we talk about the initial amount, or the y-intercept, we can also think of that in terms of compound interest as the principal. So here's the general form for compound interest, where we have A as the ending amount, P is the principal, or the initial amount. We've got this quantity 1, which we'll talk about pretty soon, and then plus this ratio of R over N, where R is the annual rate, or the interest rate, and then N is the number of times that it's compounded per year, so N times per year, and then raised to the NT, where again, N means that same number of times per year, and then T is time in years that you're compounding the interest. Okay, so let's make some sense of this. Compound interest can be modeled by this formula here, where P represents the principal. The value 1 represents 100%. So we know that if we were to write 1 as a percentage, it would be 100, or if we wrote 100% as a decimal, it would be 1.00. And that represents the rate of interest, or the interest rate. If there is a growth rate, then the R value will be positive. And if there's a decay rate, then the R value will be negative. N represents the number of times per year the interest is compounded. Okay, so the number of times per year that the interest is compounded. The growth factor is equal to 1 plus the growth rate. Okay. All right, so let's see a few examples. Go ahead and flip the page. So here we have Kimberly's family invested in a CD, or a certificate of deposit, for when she was born. The interest is compounded quarterly. Okay, so to the right, we see the CD. We have the initial amount deposited is $3,000. We have the annual interest rate is 8%, and we know that it's compounded quarterly. All right, so part A, what is the initial value? That's the amount that they deposited at the start. That answer is $3,000. At what rate will the amount increase? So we know that it is increasing by this compounded interest rate. Okay, so that's going to be 8%, which as a decimal can be rewritten as 0.08. How many times is this value being compounded per year? Well, if it's compounded quarterly, there are 4 quarters in a year, so therefore this will be compounded 4 times per year. Other problems might say monthly, in which case it would be 12 times a year. If it's daily, then it would be compounded 365 times a year, and so on. Write a model to represent the value of the CD after T years. Okay, so remembering our formula, we know, I'll write the general form up here, is A equals our principal times the quantity, 1 plus R over N, all raised to the NT. Okay, so let's keep that in mind. A is our amount, so that's what we are solving for. That's what we get out of this function. P is the principal, which we know is $3,000 times the quantity, 1 plus, well, we have our interest rate. This is written as a decimal, so we have 0.08 over N is the number of times we compound per year, and in this case, that number is 4. And then we have to the NT, so again, N is 4, and then T, this is our variable. We can plug in some number of years, some number T years, and we're going to get some amount that the account has in it after T years. So what will the value of the CD be after 16 years? So let's go ahead and evaluate. So we have A equals 3,000 times 1 plus 0.08 over 4 to the 4 times 16. So we're plugging in T equals 16. All right, so let's see what this is equal to. I'm going to go ahead and take out my calculator and start a new calculator here. So we're going to do 3,000 times the quantity, 1 plus, I'm going to do control divide to get my fraction bar. And then we have 0.08 over 4, and that's all raised to the power, I'll get out of those parentheses, raised to the power 4 times 16. Okay. So I want to make sure I type that in correctly. That looks pretty good. All right, so we're going to hit enter. So we've got $10,654.47. Okay, so 10,654, 10,654. What was the cents on that? 47.9 cents. Now I'm going to say 47 cents. Yes, you could round up and say 48 cents, but because we don't have that full cent, we can't include it into our answer. So we're actually going to round down. We're going to cut off at the cents at the hundredths place, and we're going to round down. So just the 0.47 because we don't have that 48th cent. Okay. So our total amount, and actually I'm going to just put a star there. We're going to round down. So we only have that $10,000, $654.47. Okay. All right, so number 2, determine the number of pica in a region knowing that it's decreasing 8% each year. We have the initial population is 144 picas. Write a model of the pica population after t years. So we're going to use our compound interest model because we know that it's decreasing 8% each year. So we're going to write this as A equals our initial amount, which we know is 144, times a quantity, 1, and then it's decreasing by 8%. So that tells me that we are subtracting 0.08, that 8% as a decimal. Okay? And it doesn't say that it's compounding multiple times a year. We just know that it's decreasing by 8% every year. So we can just write it like this. There's no n in this case. And then our exponent is t. Okay? Now I want to know what's the population after 1 year, 5 years, 6 years, and 10 years. All right, so let's go ahead and write out our model. I'm actually going to plug this into our calculator. So we're going to go, one easy way to do this is I'm going to go ahead and just graph this. So if I were to go to new, I don't need to save this. We're going to do a graph. If I were to plug in this function here into the TI Inspire for a graph, I'm going to do 144 times the quantity 1 minus 0.08, and then raised to the, we're going to use the variable x here. Okay, so we're going to hit enter, and I'm going to hit Control T, and that's going to pull up a table of values. Okay, so as we look at this table of values, this is saying at x equals 1, or in this case, t equals 1, this is the y value, or the a right here, the total amount. So let's go ahead and write this out. As we have 144 times 1 minus 0.08 to the 1, this is equal to 132.48. Now, because we're talking about population of a species here, we can't have a 0.48 in the population. So again, we have to round down, and we have 132 of this population. So 132. All right, for 5 years. So we would model this. I'm going to go ahead and simplify that parentheses here. So this would be 5 years. If we were to plug that in, well, let's look at our table. We have that the population here is 94. For 6 years, so 144 times 0.92 to the 6. Let's see what that is. Back to our calculator, 87. And let's do 10 years, so 144 times 0.92 to the 10 is equal to, back to our calculator, we'll see 10. We have 62. Okay. Letter C, how does the decrease in the pica population for years 1 to 5 compare to the population for years 6 to 10? So from years 1 to 5, we've got a difference of 5 years, right? Or I guess it would be 4 years, right, if we're counting year 1. Or if we're not counting year 1, then it would be a difference of 4 years. Then we have a difference of, well, 132 minus 94. So we see that this difference is 38, a decrease in 38 picas. From years 6 to 10, the same interval, 4 years, we have the difference of 87 minus 62. And we find that this difference is 25. So therefore, the population decreased more in years 1 to 5. So at the start of the 10 years that we're measuring the population, it decreases more than it does toward the end of our time measuring it. All right. Go ahead and flip the page. Here we have Mike is comparing the cost of maintaining his car with the depreciating value of the car. When will the cost and the value be the same? Please use Desmos or the Inspire to verify your answer. Okay, so we get that the value starts at $20,000 and decreases by 15% each year. The maintenance cost is $500 for the first year and then increases by 28% per year. Okay, So if I want to compare these, I have to write some models for each of these representations. So we'll start with the value. I know that the value is equal to the principal amount, $20,000, times 1, and then is decreasing by 15%. So we're going to say minus 0.15% each year. So that would be to the t. And let's go ahead and clean that up a little bit. $20,000 times, this would be 0.85. Okay. For the other one, here we have the maintenance cost is $500 for the first year and then increases by 28% each year. So we can say that the principal, the initial amount, is 500, and then we have 1 and then plus for an increase of 28%, so 0.28% per year. And then cleaning this up, we have 500 and then times 1.28 to the power t. Okay. And I want to know, when will the cost and the value be the same? So let's go back to our calculator and see when these would be the same. So I'm going to go back. I'm going to hit Control T to get rid of my table here. I'm going to hit Tab, and I'm going to go up and just take out that old function that I have. Okay, so I'm going to put into f1 of x, I'm going to put in my first. This is going to be the value of the car. So we have 20,000 and then times 0.85 to the power t, or to the power x we're going to use. Okay, I'm going to hit enter, and we're not going to be able to see it because it's going to be way off the graph, right? Remember, we're talking 20,000. I'm going to hit tab, and now I'm going to put in for f2, I'm going to put in the other function. So 500 times 1.28 to the power t, or to the power x, I should say. And we're going to hit enter there. Now, I want to see this graph here, and I want to see what's going on. So I'm going to go to my window, and I'm just going to go to my window settings, and I'm going to define some minimums and maximums. So minimums, I know that the time is never going to be negative, so we can do something small like maybe -5. I know this is probably going to occur like within the first, I don't know, 50 years. So let's go ahead and do 50 years. For the y values, we're not going to have a negative value for either of these. Both of these are going to have a asymptote at y equals 0. So again, it doesn't really matter what our y minimum is. And then our y maximum, we know that it starts at 20,000. So let's just do 25,000 and see what this looks like. Okay, great. So now I can see this graph. I see that the blue graph is F1. This is the value of the car. We can see that it's depreciating over time. We can also see the maintenance cost, F2, is increasing over time. And so I want to know, when will these be the same? So to find the intersection point on the TI Inspire, I'm going to hit Menu and Analyze Graph. We're then going to choose number 4, which is the intersection feature. And so to find the intersection between two functions, you're going to choose a lower bound and an upper bound. The lower bound is going to be an x value less than the intersection point, and the upper bound is going to be an x value greater than the intersection point. And so we're looking at these x values. Essentially what you want is to have in this middle region the intersection point. Okay, so I wouldn't want to do something over here because there is no intersection within this region. But I want to choose another point just to the right of the intersection. And I find that our intersection is right here. And so the cost is the same after about 9.01 years, or right around 9 years. Okay, so let's go ahead and write the answer. At about 9.01 years. Okay, and so that would be when both of these equations are equal. That's the t value. All right, last problem. Here we have the population of Hillville grows at an annual rate of 15%. What will the estimated population of Hillville be in 5 years? Okay, so let's go ahead and model this using our compound interest formula. A is equal to the initial value, and we know that that initial value is 5,000. Okay, times 1 plus, because we are growing, 15%, so 0.15. The estimated population in 5 years, that's going to be our t, is t equals 5. So let's go ahead and plug this into our calculator. So I'm going to just open up a new doc. And we have 5,000 times 1.15. That's 1 plus 0.15. And then to the power of 5, I'm going to hit enter. And we have about 10,056 people. Okay. So these have been our notes on exponential growth and decay. Today we talked about the compound interest model. As a reminder, is A equals the principal times the quantity 1 plus or minus that interest rate over the number of times compounded, all raised to the power of the number of times compounded times t, the time in years. Okay, we're going to get a lot of practice on this, so we'll see you tomorrow. Have a great day, everybody. Goodbye.